Hello everyone. So, in the previous video, we have discussed something about the static thrust. Now we'll discuss about an important performance parameter of an aircraft, which is the aircraft range. You might have seen this in Flight Dynamics 1 course, but again, this is like a revision. So, the aircraft range is a distance which an aircraft can travel with a given mass of fuel. Now, while doing this analysis, we'll be assuming that the flight is a level flight. That is, we are ignoring this takeoff, climb, and gliding descent phases. And then aircraft characteristics other than the total mass are constant throughout the cruise. So now for this aircraft given, the lift is equal to weight and thrust is equal to drag. Now you may have a question, why it is not T minus D equal to m dot V? Because this, what you're saying is m dot V is actually included in this thrust term itself. So I can directly say that it is thrust equal to drag. So T is equal to, I can modify it as T equal to L into D by L or mg into L by D because lift equal to weight, where I will call this L by D as aerodynamic efficiency, which is CL by CD, which is same thing, and m is the instantaneous mass of the aircraft. Now I'll write this m dot f, which is m dot or minus m dot in terms of this eta naught as given like this in terms of overall efficiency. Finally, on substituting all this in this equation, like m dot f is equal to minus dm by dt or write it as minus u dm by dx, and finally get my range as something like this. This is an important equation. This is called as the Brickett's range equation. Now, for now basically, let us discuss one important aspect. Like our range is directly proportional to eta naught L by D, correct? So if I plot eta naught L by D versus Mach number, I'll get something like this. Like this is just a qualitative graph. So and this maximum occurs at point 8 to point 9. So you may ask, you'll say that okay, my high subsonic commercial aircraft is usually used in between point 8 to point 9 Mach number. But why not a supersonic aircraft? We don't prefer supersonic aircraft because like for T naught by T equal to 1 plus gamma minus 1 by 2 into m square. You know this from your gas dynamics course. For larger Mach number, this T naught is very large. T naught is a stagnation temperature, which is a surface temperature, right? Because if some gas is flowing right here, here the gas stops and this will be a surface temperature or the stagnation temperature. So for larger M, this T naught is larger. Say it may go of the order of 3000 Kelvin or so. For this, you need to consider like heavier metals like tungsten, etc. But they are costly. If you cannot do use a lower metal like aluminum or iron, etc., because they'll melt. So finally, large commercial aircraft will usually be operated point 8 to point 9 Mach number. And then we also and then I can also write this delta x as so L by D ln m1 by m2 into tu by m dot fg, where t by m dot f is called the uh, sorry, m dot f by t is the thrust specific fuel consumption. So you can say that this range is inversely proportional to TSFC. So yeah, that's it for this video. In the next video, I will be discussing about the ramjet engine. Thank you.